companies, Gradescope, which automatically grades homework and exams, and Coherent, which I'll tell a little more about later. These days, if you read the news, you can't miss anything, can't read the news anymore without seeing anything about AI. For example, late Stephen Hawking warns AI might end mankind. Elon Musk says it's the biggest risk we face as a civilization. Then also, Elon Musk invents $1 billion to build artificial intelligence. And then articles that say the exact opposite. Why everything you've heard from even Stephen Hawking and Elon Musk is untrue. So what do you think now? Politicians are getting involved. On September 1st, 2017, Vladimir Putin gave a lecture to all the kids in Russia, telling them about how it's really important to study AI because whoever rules AI will rule the world. There's now a minister of AI in the United Arab Emirates. And also in Europe, there's a lot of momentum to try to build AI within Europe. A lot of money going into AI. DeepMind was bought by Google for about $500 million. Two of my former postdocs started a company called Otto, and after 6 months, this company was bought by Uber for $680 million. China's putting a lot of money into AI, both commercialization and fundamental research. And even the US recently started to prioritize AI research more, with a recent commitment of $2 billion for AI research. And our AI conferences have completely changed. The NIPS conference, the main conference for AI and machine learning, was sold out faster than the most popular pop concerts these days. In about 11 minutes and 38 seconds, all tickets were sold. Also means life as a professor has changed a little bit. Usually, when you're a professor, your life looks kind of like this. You kind of spend a lot of time reading and quietly answering emails and reading more stuff on your computer. But with AI being so popular, these things start to happen now. This is a dinner last April with Jeff Bezos from Amazon, who just invited a bunch of people who he wants to learn from in machine learning, artificial intelligence, robotics, and has dinner with them, tries to learn about the latest. Similar for Elon Musk, Larry Page, Jensen Huang, people I've never met until a couple of years ago. All of a sudden, they're all interested in finding out more. And the conference is becoming really, really big. 8,000 attendees these days compared to just 1,000 before. So is there some hype? Probably. But also some fundamental advances are being made. And what I want to do is highlight a few of those. A lot of the current advances are through deep learning. Deep learning actually has 3 different pillars: deep supervised learning, deep reinforced learning, and deep unsupervised learning. I'll tell a little bit about those. Then we'll look at some applications and where things are headed. So let's say you want to build a system to recognize what's in an image. It's very clear to us this is a coffee mug. But for a computer, this is just a bunch of numbers. And so this is not a great thing to write a piece of code for. Very difficult to write lines of code that say what's in an image. So people worked on this in the form of machine learning approaches. And they would say, I have an image. I transform into a new representation of an image called hog, daisy, sift, and so forth, which is essentially a histogram of where the edges are in the image, which is more invariant to lighting than just the raw pixel values, and then feed it into a support vector machine, which is the equivalent of linear regression, but for classification. Linear regression works great if your points are more or less on a line. If they're not on a line, not so good. Same thing for support vector machines. If your points are nicely separable by a line, it works great. But if the points are not nicely separable by a line, it doesn't really find a solution. It can't. Then in 2012, things drastically changed. Out of Jeff Hinton's lab at the University of Toronto, it was shown rather than building these complicated pipelines, which didn't really work, it's possible to build one big black box, in some sense, a big neural network that you can train to recognize what's in the image. And the best way to think of this neural network is as a computer program that you don't write yourself, but that has 60 million free parameters that you let it figure out on its own what they should be. and a different choice of those 60 million parameters leads to a different program. So how do you program this? By examples. You collect a lot of examples, for example, images of cars, images of cats, images of dogs. You feed them into the neural network as examples of what it should recognize in an image, and from these examples, it starts recognizing the pattern. How big a change has this been? The big image recognition competition called ImageNet is held every year, and in 2010, the error rate of the best entry with classical computer vision was about 30%. In 2011, it wasn't much better, and this was kind of flatlining. But then Jeff Hinton's group, with a deep learning approach, landed right there, halving the error rate. And it was not just a one-time thing. People switched to this approach, and this accelerated progress drastically. And actually, at this point, this competition has been retired because human-level error rates are being achieved on this kind of benchmark. Now, you might wonder, what else can it do? Well, it can actually also learn to generate full captions. So you would have as input an image, and instead of as output choosing out of 1,000 categories, as output you choose 1 out of 200,000 words, then again 1 out of 200,000 words, then again 1 out of 200,000 words, until you have a full sentence. You can even do question answering this way. Now the neural net is trained with input as an image and a question, and the output is the answer to the question. For example, how many school buses are there? And the neural net says 2, and that's indeed the correct answer because behind here, there's a second bus, and it sees it. What this really is a change in programming paradigm. The way we used to program is by writing lines of code. If, then, else, while, and so forth. And this works for some things, but doesn't work for things like image recognition. What we're doing now instead is the program lives in the neural network, and the way we write the program is not by writing lines of code, but it's by providing examples. And the set of examples we choose decides what is the program this neural network will execute. And this works really well for things like image recognition, but not just image recognition, also for things like speech recognition. We had a similar breakthrough where deep learning went right through that floor in around 2012 also. Machine translation, similar problem. Inputs, corresponding outputs, pattern recognition problem, and a neural net can be trained from enough paired up data between 2 languages, how to translate from one language into the other. So you might wonder, how long has this been around? In fact, people have been playing with neural nets since computers existed, back in the 50s. So how come this is happening now? Well, 3 main factors. Data, a lot more data today than before, compute to process the data, and also a bunch of AI innovation. So deep supervised learning is about pattern recognition, and if we have enough data that is input-output pairs, a neural net can be trained to recognize that pattern. And that's something you can put into practice, and a lot of companies are commercializing. But you might want more. Being intelligent is more than just recognizing a pattern. Being intelligent involves having goals, trying to achieve things. And that's where deep reinforcement learning comes in. If you had a robot, maybe you wanted to have it ensure your house is clean, or a meal is cooked, rather than just pattern match. It's not just for robotics. Many applications are goal-oriented rather than pattern matching oriented. And so what you want here is a system that looks at the current situation, analyzes it, makes a decision, and this process repeats over and over and over. And in reinforcement learning, the hope is that your neural net can train itself. It tries and tries and tries. Initially it fails, but over time it becomes better and better and better at solving this problem. This has actually been shown possible for learning to play video games. It's also been shown for the classical game of Go, which many people thought would take decades before computers can achieve human-level performance, but was solved in 2015. It's been shown for more advanced computer games like Dota 2. And what we're going to watch here is for the first time actual learning in action. What do we expect when reinforcement learning is in action? Initially, the neural net doesn't know what to do, so this character will just fall over. but after it's fallen over a few times, and sometimes it fell over more slowly, is going to update the weights in the network to make it more likely to fall over more slowly also next time. And that's what we're going to watch here. So initially, it falls over. After 20 updates in the network, it falls over a little later. After 80 even later. And more, it becomes capable of running in that direction, which is the goal it's being given. We don't give it any information about what walking looks like, what running looks like. We just ask it to go as far as possible in that direction, and it figures out over time how to achieve that. Now the beauty here is that you can program once a reinforcement learning algorithm, and you can reuse it for many other applications. So without changing any code, we can now swap in a different robot, let's say a four-legged robot, and now the neural net learns to control the four-legged robot. And in fact, we can swap in the Atari games. And if we swap in the Atari games, the same piece of code will train up a neural network to learn to play Atari games. And that's the beauty of the approach here, is program once, apply many times to many applications. Here's another example where it's been trained to control a line. This could be used for, let's say, animated movies or video games. And here it is in action, training a robot to put a block into a matching opening. Again, the same approach, deep reinforcement learning, but now training a physical robot. And in about 1 hour of practice, you can get the block into the matching opening. You might say, this is so easy, we can do this first attempt. But we start with a brain that's already learned a lot ahead of time. This is starting with an empty brain, from scratch, figuring out how to see things and control itself. Here's another example. This is a result at OpenAI, where through reinforcement learning, this robot hand is able to now control this block to match its orientation with what's shown on the bottom right. And this is some of the most advanced in-hand robotic manipulation to date, and it's all purely through learning. Here's another example. This is a collaboration with NASA. This is the NASA Super Bowl, a robot for planetary exploration. It's a bunch of cables and rods, very hard to control, but reinforcement learning was able to figure out how to control this robot. You might wonder why a robot like this? It's like wheels in all directions, but hard to control, and that's where the reinforcement learning comes in. So reinforcement learning is about learning to achieve goals, but it can still be time-consuming. In supervised learning, a human needs to label. In reinforcement learning, you need to supervise and say what's good behavior, what's bad behavior. It's a lot like training a dog. If you train a dog, and at the end of the day, you say good dog or bad dog, it's not going to learn much. But if you constantly tell it good, bad, then it's going to learn much more quickly. So can we go to even less supervision than we need in reinforcement learning through maybe completely unsupervised learning? In unsupervised learning, a lot of the work tries to learn about the world by generating it. So instead of going from, let's say, an image, process, a decision, it gets flipped around, and you go from a small code, and you see if even from a small code can generate something real. Okay, let's run this neural network. Here are images generated by this neural network as it's being trained. The more it's being trained, the more realistic the images become. This is for outdoor images. Here it is for... Oh, that didn't play. Is there any way to play this? Who controls the computer? Thank you. So here it is used to translate horses into zebras. And then can we play this one? Here it is used to translate one person's dance moves into another person's dance moves. So this is calibration. This is the source, who knows how to dance really well. These are two PhD students at Berkeley who don't know how to dance well, but just have to do this. If you can do this, that's enough to be calibrated and then generate your dance videos based on a professional dancer's moves. Doesn't need to be hip-hop. Here is a new professional demonstrator. This is the new calibration. And here is the automatic generation of a video of the students doing the same thing. Of course, a lot of, this is really fun. Other things to think about, fake news and so forth. A lot to worry about also. Okay, what are some applications that are currently being commercialized? Clearly, self-driving cars is one of the biggest commercialization areas. Once you can see what's around you, you can hopefully have a car drive itself. A lot of speech interfaces, face recognition interfaces, which we saw just earlier. Doctors' jobs are being automated. If a doctor's job consists of looking at something visually, a neural net can have seen many more past cases than a doctor can ever see in their lifetime, so it can probably learn to do this better. For dermatology, for radiology. Here's another example use case. Yelp, a restaurant review website. This is the old way of displaying pictures people took in the restaurant. Now a neural net has been trained to recognize what are appealing images to make it look more interesting, automatically selected. Emojis. When you're typing, there might be thousands of emojis in your emoji vocabulary, but you want the relevant ones where you just typed. Can you predict which are the relevant ones and make those available? And in my own life, what I've been pretty interested in is to now start commercializing robotics. Now that we can process the sensor information, we can have robots do much more intelligent things. If you look at old school robotics, it's about the same motion over and over and over. But now that robots, in principle, can see, I see two new waves of automation coming. Wave one is robots with eyes that understand what's around them, and based on that can do a much wider range of skills. And I think wave two will be one about 5 years from now, where we'll see robots that can be taught new skills on the job. So you wouldn't buy a robot for one job, you'd buy a robot because you need physical labor, and you'll teach the robot whatever's needed as time goes about. The company we started is called Covariant. We're focused on both of those, the short and the longer term, and very much looking at industrial automation, logistics, warehousing, hopefully in the future some of the things alluded to earlier, construction and farming, but for now mostly warehousing and manufacturing. So those are some of the current things. I want to leave you with some longer term parting thoughts. So a lot of people wonder, is a new AI winter coming? Because we've had an AI winter in the 80s, 70s, 80s, where things quieted down, and right before that, people were just as excited as we are today. Well, let's think about what is causing the excitement right now. It's data, compute, and innovation. Innovation is a matter of smart people. We'll still have smart people in the future, so that's not going to be the bottleneck. But how about the data and compute? Well, there's ever more data being generated every day. So that doesn't seem like it's going to stop anytime soon. How about compute? There's Moore's Law, but some people debate whether it might be slowing down or stopping, so it's not as clear whether we're going to continue to get compute improvements through Moore's Law. But other things you might benefit from. Well, one thing is that Moore's Law is all about making transistors smaller. But it's still, in this graph, all CPUs, GPUs type things. What if you lay out transistors more dedicatedly for neural networks? A bunch of companies are working on that, and they're claiming that if they are successful, they can provide 100 to 1,000 times the compute in the same chip size, just by laying out the transistors in a more clever way. Not making them smaller, it's an orthogonal way of making progress. Thinking about Moore's Law, doubling every 3 years, 1,000x would be 30 years of Moore's Law. So if they succeed, that's going to be a drastic increase in compute. It's not the only way to increase compute. Another way to increase is to network more machines. If you look at some of the breakthrough AI results of recent times, AlexNet is right here, and then AlphaGo 0 is up here. Just a few years later, 300,000 times more compute was used in just a few years. And that's by networking more and more machines to get your results. So it looks like we are on an upslope still in terms of compute. And a lot of companies are making a lot of money through AI, which means that will keep pumping more money into AI innovation. So personally, I don't see an AI winter coming anytime soon, given these enabling factors seem all on the up ramp. So let's take a look at scale in terms of how far we're along. Let's see, a fly has about 100,000 neurons. Let's put this in perspective. AlexNet, the neural net from 2012 from Jeff Hinton's lab with the big computer vision breakthrough, has 650,000 neurons. So it has more neurons than a fly. So what that means is that we're already building pretty big neural networks. It also means that we're not building them very cleverly. Nature's design is better than our design. A fly lives a much more interesting life than AlexNet and has a smaller neural network. A mouse has a bigger network though, 100 million neurons, and human has 100 billion neurons. Now what matters for compute is the synapses. The synapses is where two neurons are connected. And a synapse can either fire or not fire roughly once per second. So that means you have one floating point operation per second per synapse. So maybe if you're a lucky human with upper end of the spectrum number of synapses, 10 to the 15, you have 10 to the 15 floating point operations per second in your head. So if you want to put a human brain compute in a box, we need a box with a petaflop of compute. Can we do that? Not yet today, but maybe we can do it with many machines. Well, if you rent 10,000 CPUs on Amazon's cloud, it'll cost us about $1,000 an hour. We can rent a petaflop of compute. We can do it with GPUs more cheaply. With GPUs, we can do it for $30 an hour on Amazon, $25 an hour on Google Cloud. So for $25 an hour, we can get human-level compute in the cloud. Not the right software, but at least the amount of compute. This might cause a lot of reason for concern, because as these prices keep going down, probably in 5 years, it's below minimum wage to get human-level compute in the cloud. If that concerns you, which would be good if some people are concerned and worry about this, here's a book that you might want to check out. Second Machine Age looks at what happens when we have drastic changes in human productivity. It used to be we gather food and we hunt, then we became farmers, then we had the Industrial Revolution, and now we'll have the Intelligence Revolution. And so the question is, what's going to happen now in terms of job displacement, job destruction and creation, and how are we as a society going to deal with that? A lot of non-technical questions that are going to be very hard to answer, but very important to answer. Now let's assume we get through that. Let's say we are, as a society, capable of getting through this whole revolution. Then the superintelligence idea becomes important. This is a book by Nick Bostrom. He's a philosopher at Oxford University in England. And the question he looks at is, if we were to build an AI, next day it's going to be smarter than us. And that could be a problem. For example, today here, who has paid a lot of attention to the life of ants? Probably nobody. But the intelligence of ants will be to us like we are to the intelligence of some superintelligence, and the superintelligence might not pay a whole lot of attention to us. Which might not be the worst thing in the world if it doesn't pay attention to us. It's worse if it doesn't like us and pays a lot of attention to us. What the book is about is really about this notion that there's actually something fundamentally different about the superintelligence relationship with humans than humans with ants. And the difference is that we get to build the superintelligence. And so the question is, as we are building it today and in the coming years, how are we going to build it such that it actually cares about us and leads to good things for us, rather than just maybe ignores us or even might compete with us over resources. If you want to learn more about AI in the ensuing time, I would highly recommend you subscribe to this newsletter. It's a newsletter written by Jack Clark. He used to run the AI beat at Bloomberg. Now he's communications director at OpenAI. Every week, short summary of what's happened in AI, technically, commercially, politically. Very quick way, 5 minutes a week, to stay up to date on the latest developments. Sorry. That's it for me. Thank you.